Hello everyone. Sorry this video lecture is a little late. I literally just finished my last lecture, so I'm diving right back in so I can get it to you as soon as possible. So we, in our most recent lecture, just went over hypothesis tests, which are a very major topic, and I'm hopefully going to give us a lot of practice. In addition to the practice, I am giving us this next example. So, suppose a community college hired a consultant who claimed that the average student housing expense was $650 a month. The community college is skeptical of this value so they take a simple random sample of 75 students and find the following. They find their sample mean to be equal to 611.63. They find the sample standard deviation, and this is going to be a new thing, so don't freak out. But if you take the sample and you plug everything into that standard deviation formula that we've gone over at the beginning of the semester, the sample standard deviation, which we often note as S, they found it to be 132.85. So something to note here, we don't have the population. Standard deviation. And this is something I think actually some of you noticed is that I've sort of been sidestepping. I've been kind of giving you the population standard deviation, even though in real life, this isn't really something that we would know, right? It doesn't, if we can't collect every single data value to get the actual population mean, why would we assume that we knew the population standard deviation? Because knowing this value would also require us to collect every single data value out there, which again, it's not feasible. So in this case, we don't know the population standard deviation. The college collected their sample, found a sample mean to be 613.63, found their sample standard deviation to be 132.85. And what I'm going to tell you is plug in the sample standard deviation for the place where we would usually put the population standard deviation. But I'm going to put a little bit of a wait and think about this for a second, and I'm going to return to this. So let's go ahead and finish our hypothesis test using the sample standard deviation, but I have a number of comments to make about this when we get to the end. So we need to know the standard deviation of the mean, right? Which is just going to be equal to the standard deviation of the population divided by root n. We just said that we're going to plug in our sample standard deviation for the population standard deviation. And I put this here because this is technically, we're approximating the standard deviation of the population. We're approximating it with the sample standard deviation. And we can proceed forward. So 132.85, our sample was 75, right? Which will put us at $15.34 as our standard deviation for the mean. Okay? So we want to make a hypothesis test. And to do a hypothesis test, we need X bar to be normally distributed. Because what we want to do is we want to make that confidence interval, right? And then use the confidence interval to perform a hypothesis test. But yet again, as I've mentioned a few times now, if we want to do a confidence interval, we need to first know that X bar is normally distributed. So let's assess whether or not it is. Let's look at the data. So this is our data. So student housing prices. And we note a moderate skew, right? It looks like it's moderately skewed to the right. That the observations are randomly sampled, right? I'm checking my points for the central limit theorem. I'm also just going to tell you in this case it was less than or equal to 10% of the total. So we have independence, simple random sample, less than or equal to 10% of the total, we're good. We do note a moderate skew, but our sample size is sufficiently large. It's 75, that's big enough. So I would say in this case that our sample size is large enough to overcome the fact that there does appear to be a skew. If there was a really, really strong skewed, I might revisit that assumption. But in this case, X bar is approximately normally distributed. Okay, so let's see. We want to do a hypothesis test. So let's start with our first step, which is define our hypotheses. We wish to know if the true average housing expense of students coincides with what our consultant claimed it was. So the consultant claimed it was $650. So our null hypothesis is that the true population average is $650 against the alternative that it isn't. Okay. Step 2, we took a sample. And we got that X bar was equal to 611.63. And then we did this sort of magic mumbo jumbo to say that this was equal to 15.34. Okay. So that was step 2. Step 3, build a confidence interval. So we want, I think in this case, we want to do a 95% confidence interval. So I'll do 1 minus 0.95. Alpha is equal to 0.05. My C is going to be equal to absolute value of the alpha over second percentile, which is Z of 0.025, which is going to be equal to 1.9699, around there, or 95, excuse me. I think I put this was, oh goodness, I told you I did it by memory in the last class, and indeed I did. It looks like it's this actually. I put 6 in the last lecture. It should have been a 5. I'm so sorry. You should go back and change your notes. So that's what all of these numbers are, and I believe with these things we have all we need to calculate the confidence interval. It's going to be 611.63 plus or minus 1.95996 times 15.34, which gives us 58. We are 95% confident that the true population value falls in this interval, which is equivalent to saying if we were to make this interval, take a bunch of samples and make this interval a ton of times, we would expect that approximately 95% of confidence intervals made in this way will contain the true population average mu. So step 4, we made our confidence interval. Step 4, take a look. Is mu, all right, so it's a, is the null value in here? The answer is no. The consultant said 650, right? So since 650 is not in our null hypothesis, we reject the null hypothesis. And perhaps hire a new consultant. So let us go back to the major note I made at the beginning, which is we didn't know. So we were able to do our whole process, but we didn't know the population standard deviation. Here. So we used its point estimate the sample standard deviation S, and continued forward. So how good of a thing was this to do? Is this sort of a reason? I mean, perhaps it's a reasonable thing to do. We didn't know what the standard deviation was. We need it to our calculations, so we plug in our best guess for the standard deviation. Sure, but what sort of repercussions does that cause? And when can we do that, and when can we not do that? So the sentence is, this next section is using the sample standard deviation rather than the population standard deviation. And the main point here is that realistically, we will likely not know the true population standard deviation sigma, just like how we will not know the true population average mu. we can simply use our sample standard deviation in place of the population standard deviation if we would like. However, note two things. One, for the sample standard deviation to be a good enough estimate, our sample must be large enough. Oh, excuse me, I shouldn't have said it like that. Our sample must be large enough, which our convention is greater than or equal to 30 as our sample size. So note that one of the assumptions of being able to make the substitution is actually an assumption that we are making anyway, because we are often using the central limit theorem in these cases, right? If you don't have the population standard deviation, sure, you should predict what it is with the point estimate and move forward. But make sure your sample is large enough so that your sample standard deviation S is a good guess, so that it's close to the truth. And this happens when your sample is large enough. So, so there's a little bit of a caveat here. You should do it when you have a large enough sample size, but note that there is a case where we can do confidence intervals and don't have a really large sample, and that's when our underlying distribution was normal anyway. So we get automatically that X bar is normal, so we don't need a large sample, we can go ahead with confidence intervals. Well, if that happens, and you don't have the population standard deviation, hold up, because you do actually need a large enough sample so that you can make this a substitution. Of course, if you're using the central limit theorem anyway, it's sort of a moot point. Go ahead and plug it in, because there's sort of an overlap of assumptions here. The other thing to note is that this estimate may reduce the accuracy of your confidence interval and hypothesis test. And we will show, so this, this kind of sucks. We don't want to reduce the accuracy. We want to say that we're 95% confident and mean that we're 95% confident, rather than say we're approximately 95% confident, right? So this being said, we will lose accuracy if we do this, but we will show how to avoid this reduction of accuracy once we learn about the t distribution. So this is an upcoming topic. It's actually a topic we're going to do after the second midterm, so don't worry about it too much now. But note, it does stink that we're losing accuracy by plugging in the sample standard deviation, but there is a way that we can get it back. So there is hope, but it's going to be a later topic. We need to get a little bit farther with the stuff that we're covering so far before we can really understand that. So the last thing I want to do for this video lecture is I want to teach you another cheat sheet method for these confidence intervals, which hopefully will help. Again, we're doing a lot of different we're doing a lot of different calculations, right? So it is generally a good idea to look at these to build an Excel sheet that really kind of helps you do these things fast and easy. So this is what we did last time. We did a bunch of stuff for our distributions. Let's do another one that is a confidence interval for X bar. Okay? So what are the inputs that we need? We need our sample mean. So I'm going to call it X bar, or the sample mean. The sigma, the standard deviation. N, which is the sample size. And the confidence level. Let's see, how should we do this? Which was that alpha value? Okay. So these are the 4 things we need. What outputs do we want? We just want, we're making a confidence interval. I think all we really want is the upper and lower bounds of the confidence interval, right? So our 2 outputs will be lower confidence bound and upper confidence bound. Let's make this a little bit nicer, right? I'm gonna say this is the standard deviation of the population. But note, as I just said, you can plug in the sample standard deviation here, but note it's gonna reduce your accuracy. All right, so these are the things that we want to put in, these 4. So I'm gonna make them yellow. And these are gonna be our outputs. I'm gonna make them light blue, right? Yes, so let me think about how I want to do this very well. Yeah, okay. So I'm gonna start by just putting in some numbers here so we don't get errors when we go through. So maybe this, and maybe like 30. And maybe I want my confidence level to be 0.5, which corresponds to the 95% confidence interval, right? So what is the lower bound gonna be? It's gonna be X bar minus the absolute value of the alpha minus tooth quantile of the standard normal distribution. So that is norm.s.inverse of the confidence level divided by 2. So I want that value, that's my C value, and I want to times it by the standard deviation. You know what? I'm gonna go back here. I'm gonna say we want to add some more stuff in here. Excuse me. Let's say our output is our C value, right? We want to know our standard error. Our margin of error, our width. What else? That actually might be it. Yeah, let's use all of these. Excuse me. Maybe I should have planned this out better. So what is our C? It's going to be the absolute value of our norm.s.inverse function of our confidence level divided by 2. Just exactly that. That's looking good. Our standard error is going to be our standard deviation divided by the square root of our n. Think so? Yeah, doing this in more steps was better. I was trying to squeeze it all into one formula. Our margin of error, that is just going to be equal to the C value times our standard error. Our width is just going to be 2 times the margin of error. That one's easy. Our lower confidence bound is equal to X bar minus the margin of error. And our upper confidence bound is equal to X bar plus our margin of error. Okay? So if I got a sample and my sample got a sampling of 5, and I knew that my population standard deviation was 2, this right here is the confidence interval that I would build for the true population average. So maybe I should say not for X bar, it's around X bar, it's the confidence interval for the population average. Gotta catch myself. Looks like I'm making mistakes today. I'm so sorry, everyone. Probably a consequence of me trying to rush this to get it to you all on time. And I'll do what I always do, which is make it nice and pretty. At least I think it's pretty. And we'll do this. Yeah, okay. And that's how you can do the same thing for confidence intervals. And hopefully that'll help you all with your calculations moving forward, and as you begin to do more and more and more and more and more hypothesis tests. All right, I'll see you all tomorrow. I'm sorry this video was so late. Let me, oops.